In this section of the course, we're going to start taking a look at the idea of what is a predicate and what is a quantifier and how can we utilize those in pursuit of our knowledge of our sort of logical statements. And so in this section, things that you can expect to see, we can expect to see truth sets and the verification of truth sets. You can expect to see the quantifiers, and quantifiers are going to be universal, existential, and conditional, and even multiple quantifiers. And then after that, we're going to learn about the negation. And along with the negation, we're going to learn about the converse, contrapositive, and the inverse of some of our conditional statements. And then we're going to learn about verifying these sorts of statements, or the sorts of those sorts of predicate statements. All right, so that's what you should expect to see in this section. So let's start off with the idea of a truth set. And before we can start off with a truth set, we have to start off with some sort of sentence that contains a finite number of variables that becomes a statement. And remember, a statement is either true or false when you insert values, when specific values are substituted. That's called a predicate. So our predicate is our statement or our sentence that's either true or false based on the domain. And we know that the domain is all the values that we could substitute into a predicate and still get an output, not necessarily a true output, but some output. And then the truth set is going to be all the values in the domain that are going to make the predicate valid. So let's start by taking a look at a really basic example of how we're going to work with some of these sorts of ideas. And so at first we have this predicate. So we have the predicate P of x is equal to x greater than or equal to 1 over x. All right, so that's what our P of x is equal to. And the first thing we want to do is we want to write P of 0.5 and P of 1 and determine if it's valid or invalid. So for the first statement, well, P of 0.5 is going to be equal to 0.5 greater than or equal to 1 over 0.5. Or that's the same as saying 0.5 is greater than or equal to 2. And clearly that's false, right? So that's what we mean by a predicate and substituting a truth value into that predicate. All right, so we write right away that P at 0.05 is false. Now P at 1 is going to be equal to 1 greater than or equal to 1 over 1, or 1 greater than or equal to 1, which is a true statement. All right, so those are the truth values, and we know that all numbers are in this truth set except for 0, or I'm sorry, all numbers are in the domain except for 0 because we can't divide by 0. Now, we're asked to find the domain of x, where x is in the real numbers, negative real numbers. All right, so right here, whenever you see r minus, that just means negative real numbers, and we want to try to find the truth set of P of 1. All right, so here's what we could do. We might be able to just play around with this and maybe find some numbers that work and don't work. Okay, so if this is part A, then part B, we know that P of 1 works, but that doesn't matter because we're looking at the negative real numbers, right? So let's try numbers like maybe P at -1, and we could try and see if that works. And P of -1 is going to be -1 greater than or equal to 1 over -1, and that's true. All right, so right away we know that's in the truth set. Now what about P at -0.5? Right, so we're going to get -0.5 greater than or equal to 1 over -0.5, or -0.5 is greater than or equal to -2, and that's true as well. So right away, if we kind of think of this as a number line, and I'm going to draw a number line up here just to make it a little bit easier for us. If we think of a number line for this, so here's 0, and here's 1, or +1, and then here we have -1. It looks like that 0.5 is okay, or -0.5, so that's okay, and 1 is okay. right? Now we know 0 can't be in the domain of this because we can't divide by 0. Now let's try something like p of 2 or negative 2. Well, that's going to say that negative 2 is greater than or equal to negative 1/2, all right? And clearly that's false, right? So we know that this is false. And so what we're seeing is that there are a set of numbers that makes it valid and not valid, all right? So it looks like right here, p of 2 is not valid, 0.5 and 0.1. And so it looks like to me that this is basically the domain, because we know that negative 2 doesn't work. And if we were just inspecting it, negative 3, negative 4, negative 5, even negative 1.5, right? All of these numbers are going to be false. So essentially, what you can do is you could just use trial and error to be able to figure this out. So if I was to ask you for the truth set for this, or the domain for where it's valid, then what you would say is that X would be an element from inclusive negative 1 to 0. All right, so now what about on the other side? All right, so let's get rid of this stuff. We know that that's all true, but we still need to make sure that we can figure it out for x's in all real numbers. Right? So we already know it for the negative side. That's taken care of. All right, so right away we know that x is an element from negative 1 to 0. But let's try some other numbers. All right, and we know that net positive 1 works. Right, because remember we did that up here, and that was good. 0.5 did not work. Right, and think about this: if you divide by any number between 0 and 1, 1 over that number is going to get bigger. So 1 over decimal point 0.01 is going to be greater than 1, and 1 over 0.9 is greater than 1. So it just looks like that none of the numbers to the left of 1 are going to be useful for us. Right? But let's try something like 3. Right? So p of 3 is going to be equal to 3 greater than or equal to 1/3. And that's a true statement. P of 4, 4 greater than 1/4. And that's a true statement. So it looks like all of these numbers are valid. And so for our truth set, we're going to combine that in the real numbers with 1 to infinity. Right? So it just looks like the numbers between negative 0.5, negative 1 and positive 1 are going to be excluded from our set. Right? So we just have to be careful with that sort of thing. All right, so this is our truth set for item B, and this is our truth set for item C. Right. Now we want to build up some of our syntax, and one of the things that we can start working on is the idea of the universal quantifier. All right, so universal quantifier, whenever you see this upside down A, that means for all, or every, or something of that nature. Okay, and a universal statement is going to follow this pattern. For all x in domain D, predicate Q of x. Right? Now, it's only true if all the values that you can insert for x is true in the domain D. So in other words, if any one of those values is false, it's called a counterexample. Right? So counterexample is used to prove it false. Exhaustion is used to prove it true. Right? So exhaustion means you just go through every element in the domain, and every element is true for the universal statement. All right. And it's actually pretty easy to do this. It sounds like a lot of stuff at once, but it's not too difficult. Now, the existential quantifier means that there exists, or there is at least one, or you could even say some. There's lots of ways that you could write it, right? But the existential quantifier is the backwards capital E, and the way that we write one of these statements is that there exists x in D, in domain D, such that Q of x. All right, so most of the time, just use there exists, and then for all, just use that for the upside down A. All right, so the last thing we're going to do is we're just going to write a few statements symbolically using the existential as well as the universal quantifier. All right, so let's go ahead and write these statements. So all cats are mammals. Okay, so the way we can write this is that for all x in the domain of cats, okay, so remember we have the for all x in D, P of x, right? So that's our universal statement, all right? So for all x in cats, x are mammals. Right? So that's how we would write this first one, all right? Not too difficult. For the second one, every integer is a real number. So there's two ways to write this. We could say for all x in integers, x is a real number. Of course, we could use this symbolically. Okay, so another way that we could write this is that for all x in the element of integers, and integers is denoted by z, x is an element of the real numbers. All right, so now make sure you know both. All right, and in fact, in another video, what I'll do is I'll define all of the sets of numbers. All right, so that are the shorthand ways. So real numbers, integers, rational numbers, that sort of stuff. All right, so this is for the first two. Now recall that there are, or there is at least one, that's the existential quantifier, and that's there exists x in domain D such that P of x. All right, so we have to be careful with the existential, we need the words such that rather than the comma. Okay, so there exists x in D such that. So there are students that study math. So we would say that there exists x in the domain of students such that x studies math. Right? So that's not too difficult. And then finally, the last one we have, there's at least one bird that cannot fly. So we would say there exists x in birds such that x cannot fly. And again, we don't care if the statement is true or false, or if the predicate or whatever it is, the statement that we're looking at. All we care about is just writing it. Okay, so that's the first thing that we have to do. Now, what I'll do in the next video is I'll show you how to prove or disprove these types of statements. And I'll also go through the list of the shorthand notation for the different sets of numbers, because that's going to come about a little bit later in the course.